Hello, my name is Ravi Poddar, and I will be talking about maximizing EDA simulation performance and increasing parallelism. A little about me. I am the Director of EDA and High Performance Computing Solutions on the FlashBlade product team at Pure Storage, and I help basically develop optimized solutions for EDA, semiconductor, HPC, and AI use cases. Prior to joining Pure, I actually used to be a Director of Engineering, and I've basically done a lot of tape-outs. I'd like to start talking about data and compute trends at semiconductor customers. Advanced technology nodes and increasing design complexity are driving huge increases in storage, compute, and software licenses. Large designs now are taking petabytes of storage. In fact, we heard from some of our mobile customers that some of their advanced node mobile SoCs are taking over 3 petabytes for their new designs. Compute requirements are growing at over 20% per year, and compute grids of over 50,000 cores are becoming very common. If you take a look at the graph here on the right, this is actually from Intel showing how their compute and storage needs have grown year over year, resulting in 2018 at least, of up to 1.6 million cores in their compute grid of 229 petabytes. They have seen about a 35% annual growth. And while Intel is probably an outlier, it is in line with what we hear from other customers. So because of this massive growth in compute and storage, one of the things that everyone needs to do is make sure they are maximizing the utilization of their data center resources and basically increasing and making sure they have maximized the ROI on their EDA licenses. So one of the things we always need to do is see what are the options, what are the available low-hanging fruit for improving our overall utilization. This is a high-level chip design flow. It's basically front-end, back-end, and manufacturing. I don't need to go into the details for this audience. But essentially, each side or each phase has a different I/O profile. Front-end design tends to be very high concurrency because of the huge number of simulations that are run. It's small file dominated. In fact, most of the files we see in chip design are under 8K in size. It is metadata intensive. The I/O pattern is mixed between random and sequential. And the other interesting factor, which many people do not know, is there's a very large number of deletes that must be supported, and deletes are difficult for storage devices to do. The backend design phase, on the other hand, is less concurrent, although there are new applications and new EDA tools coming out that are really trying to push the limits of concurrency and, say, the timing side, but still much less concurrent than front end. The I/Os and the data sizes are much higher than usual. I mean, everyone has seen massive spec files and defs and lefts and things of that nature. The workloads tend to be then much higher bandwidth. And so it's not uncommon for storage devices that need to be pushing multiple gigabytes per second to meet the needs of the tools in this area. And the jobs tend to be much longer running. This is a picture of an EDA farm, or an EDA factory or grid, as you may call it. But essentially what it looks like is users, they submit jobs to a job scheduler like LSF or Univer or something similar, which then submits the jobs to one of the thousands of cores that are available in the compute grid. And these compute cores then read and write to relatively few devices. Now, it's often the case that you are reading and writing from a single project, or say a particular design is very hot, and so you're doing a lot of simulation on that one project, and that project resides on a single storage device. So it's very easy to get this funnel type effect where you have thousands of cores reading and writing to one device, and that storage device tends to get saturated and then gets pretty slow. So what happens under high concurrency? Storage saturation can actually have a big impact on runtime. And we've actually seen this in experiments with customers and even in our own labs, where if you take a particular job, say it's a Git clone, and you run lots of them in parallel across your farm, runtimes can stay pretty consistent for a relatively small number of jobs. But then as you increase the parallelism, you can see this hockey sticking kind of effect where runtimes tend to get very, very large. Now, with traditional storage architectures, this is not something that is easily addressable, and it's a problem which everyone runs into. And the thing is, they may not even know it, right? So you're used to running these parallel jobs, and you're used to seeing runtime be whatever X. And so you would not even necessarily think to look that the job runtimes could be a lot less if your storage is not getting saturated. One way to test storage saturation is to run some test jobs. For example, parallel Linux kernel builds are a really good type of job that you could run to see if your storage is saturated or what the knee of the curve is. In my case, I ran some tests in our lab. I used a 15-blade FlashBlade, which is a pretty small system, but that's what I had available. And my compute cluster was 25 servers or 500 physical cores. Now, I ran up to 100 parallel Linux kernel jobs, all with J6. And you can see the runtimes here on the left-hand side. You can see the runtimes basically did not vary at all, except when I got to 100 jobs. And the reason I ran out, or reason the jobs got slower here is because I ran out of compute. At 100 jobs, I needed 600 cores, and I only had 500 available. If you look on the right-hand side, this is a snapshot from what we see from the storage device from the FlashBlade itself. And you can see the other IOPs got to 986K or close to 1 million. Those other IOPs are for us are metadata IOPs. And so this is actually a quite remarkable number showing that 1 million metadata IOPs were served by the FlashBlade. And if you look at the graph above that, it shows latency at an average latency of 70 microseconds. So very good performance. So I'd like to just reiterate, this is a great test, which I recommend people run to see what is the level of saturation of their storage device in their environment. So what storage characteristics are critical for EDA? We need seamless performance and capacity scaling under increasing parallelism. We always are adding compute nodes, so we have to make sure our storage devices can keep up. We need to be able to handle varying I/O profiles from high metadata to high bandwidth to be able to support all phases of the chip design flow from front end to back end to tape out. Support for very large compute farms. It's somewhat basically, you need to be able to support lots and lots of individual TCP connections and IP connections from your various compute nodes. And you need to have the ability to handle enormous file counts, be able to delete efficiently, and handle very large namespaces. EDA tends to be high file count dominated. And actually, a profile we took with one of our customers showed that 96% of all files were under 8K in size. And so this can result in single volumes or single file systems having billions and billions of files. So being able to handle that namespace efficiently is very, very critical. FlashBlade, which is the storage product in which team I belong, is a all-flash scale-out, fully distributed storage system, and it's designed for these highly parallel use cases. Just really quickly, the FlashBlade is made up of lots of little blades, and the blade is shown here on the bottom left-hand side, which has a storage complex and a compute complex. The storage complex is the green part, and the compute complex is the red part of this particular circuit board. First thing you will notice is there's no SSD. We actually read and write to flash directly to get the maximum performance, and it also helps us manage things like wear leveling at a system level. The FlashBlade is a fully distributed scale-out architecture, so you can think of, you can have from up to 150 of these blades working together to form a particular storage cluster. And that gives us a lot of parallelism, a lot of performance. We actually have customers today, we have customers today reporting over 65 gigabytes per second in performance and millions of IOPs. As I mentioned, it's deployed in production today up to 150 blades, running entire workloads from RTL regressions all the way through tape out, and doing as well software development and regression and library and IP memory characterization at the same time. FlashBlade is designed for EDA, and it's been deployed in many customers running the entire chip design flow on a single platform. No need for customers to start breaking up front end from back end to tape out. The system has enough bandwidth to support all these flows in parallel. In fact, from a performance perspective, it can support up to 75 gigabytes per second throughput and over 24 million metadata IOPs. From a capacity perspective, it can handle up to 10 petabytes in a single namespace, and all in a single rack, actually in about half a rack of space. FlashBlade, as I mentioned, is designed for high concurrency and EDA. In terms of the level of concurrency we've seen up to 30,000 concurrent core accesses from thousands of individual IPs at a particular customer. That's at a single instance in time. Exceptional metadata, small and large file performance, linear performance improvement by adding blades, exceptional performance for non-cacheable workloads because we actually do not cache any data inside the FlashBlade at all because the data path is so fast. We have a few very unique features. One is what we call fast file delete, or fast remove functionality, in which entire trees of data can be deleted essentially instantaneously. For an experiment, I actually created a tree of over 1 million files taking up 5 terabytes of space. And I was able to just basically move this entire tree into fast remove, and the prompt came back immediately and the space reclaimed in about 3 minutes. We also have a unique set of tools called the RapidFile tools, which are fully parallelized versions of standard Unix tools, which give you up to 60x performance, the regular Linux counterpart. FlashBlade has been very successful in EDA and chip development, and as of today, we have over 25 customers in production with over 60 petabytes deployed. Customers are seeing this have a big impact on their overall throughput and efficiency. As an example of that, I thought I'd just highlight a few use cases. One of our customers has reported over a 10x runtime improvement. Jobs which used to take over 8 hours are now finishing in like 20 minutes. One of our large semiconductor customers has reported over 200 million more simulations going through the LSF grid per year. You can only imagine what that means in terms of ROI on EDA licenses, the ability to do more design starts, higher design quality. A particular customer of ours who's in the FPGA space is achieving over 3 million IOPs on a FlashBlade system for software development and AI use cases, and the list goes on and on. The RapidFile Toolkit is basically the parallelized versions of Unix tools, as I mentioned before, and it's really providing some game-changing performance in these high file count environments. For example, the tools we have on the left here, for example, LS has pure LS, Find has pure Find, all the way down the list. They are making big improvements in overall work processes. I did some experiments using the Android code base, which is 770,000 files. And these were the kind of improvements I saw. So for Find, for example, I saw a 35x speed up, LS minus LR 38x, chmod 36x, and RM. And this is different from the fast remove. This is a file-based single RM, 37x speed up on that as well. So as I mentioned, scaling, the ability to flash for storage to perform well under increasing load is very, very important. So we actually ran some scale tests in our lab to see how FlashBlade would perform under a 7-blade, a 15-blade, and a 30-blade configuration. And what we used was actually several different profiles to generate the load. One was a read-only, metadata-only profile, which is roughly 99% metadata. A front-end design profile, which was 85% metadata, 15% read-write, and a mixed profile, which is front-end and back-end, which was much higher on the bandwidth read-write percentage. So basically, we ran these profiles using essentially standard load generation methods, and these are the results we saw. So for the read-only metadata profile, we got exceptionally good scaling from 7, 15 to 30 blade, and we achieved over 2 million NFS IOPs at the 30 blade level, which is really a remarkable number. For the front-end only profile, which was 85% metadata and 15% read-write, you can see the red line in this case was bandwidth. We achieved exceptionally good scaling on the bandwidth side. Again, almost perfect. And on the IOPS side, we also achieved over 1 million IOPs in this case as well. And for the backend profile, which was heavy bandwidth, we actually, again, here achieved over 10 gigabytes per second, almost scaling perfectly from 7 to 30 blades. So the overall result, the overall takeaway was actually really good, showing that as you increase load, simply by adding blades, you could get FlashBlade to give you almost linear performance improvements. which is really important in most EDA high-performance computing type use cases. As an example of some real workloads and the FlashBlade is deployed, and this is a customer with a 300,000 core compute farm running basically the EDA mixed profile using both front-end and back-end workloads on a single array. You can see this had over 224,000 unique IP port connections in a 2-hour period, peaking up at 14.5 gigabytes per second. Now, what's unique here is that even though this is a front-end, back-end mixed workload pushing a huge amount of bandwidth, it still was over 80% metadata. So again, extremely good performance. This is not actually an EDA profile, but this is actually from a customer doing deep learning training on the FlashBlade. This customer is a very large social media company doing training across video data, audio data, just text messages and things of that nature. And you can see here, over a multi-day period, the x-axis is May 8th to May 11th, this device served up a peak of 48 gigabytes per second, averaging about 30 gigabytes per second, but also serving a very high rate of IOPs at the same time. The ability to do both of these simultaneously is quite unique. And this was actually exceptional performance the customer was very happy with, because it was able to keep its multi-thousand GPU farm busy with almost no IO wait. Just to give you a perspective, this kind of performance, we're serving over 2.5 petabytes of data in a 24-hour period. This is another example I'd like to show you. This is a customer doing nothing but 7 nanometer and 5 nanometer tape outs and backend processes. This is out of 75 blade FlashBlade, and you can see here again, over a multi-day period, this customer is running very high bandwidth, peaking up at almost 65 gigabytes per second, and also 500K IOPS. So again, this customer is seeing some exceptional performance using FlashBlade today. I'd like to show you another picture or another snapshot of a FlashBlade running EDA backend and tape-out workflows. This is a 75 blade system doing just 7 nanometer and 5 nanometer tape-outs on backend processes. I'd like to show you another snapshot of a FlashBlade just deployed in EDA backend processes and tape-out. This is a 75 blade system doing processing on a 7 nanometer design. You can see this system peaked up at about 65 gigabytes per second and almost 500K IOPS, delivering basically game-changing performance to this customer and helping them tape out quicker. In terms of takeaways, just FlashBlade is providing game-changing performance in high-performance EDA environments. It's being able to hit multi-million IOPS and 65 gigabytes per second in real workloads. It has linear scalability. Literally, by adding blades, you're able to get more performance on your existing workloads. And you can actually upgrade it live and non-destructively. So if you're having problems, you can go from 7 to 15, 15 to 30, 30 to 45, what have you, and get that increased performance to your workloads. And of course, it also has very good API support, which allows you to have very easy integration into third-party tools to basically analyze the system very cleanly. Thank you.